today I would like to talk about power management for IoT applications. I will tell you first of all, I'll give you a short introduction about Richtek, because maybe not everybody knows who Richtek is. And after that, we directly go into a IoT application example to give you a very clear idea what kind of blocks all come together. We'll discuss a bit about the key points for power management in IoT applications, and I will take one of the IoT building blocks from the Richtek portfolio, and we really go into the lab, and I will show you some measurements and things that you have to take care of and can change in order to optimize your power management application. And finally, we will have some time for question and answers if there are any. First, about Richtek. Richtek is a analog IC design house. We are located in Taiwan, and Richtek is this year just 20 years old, so we're still quite a young company. We are doing most of our business in Taiwan, and this is maybe the reason why you haven't heard about Richtek, but since 10 years now, we are also doing the Europe region. We have about 1,000 employees. Most of them are engineers. And we are a fabless design house. It means we are using a fab of Taiwan Semi, TSMC, which is one of the biggest fabs in the world, which is just around the corner of Richtek. Since 2015, Richtek was acquired by MediaTek. MediaTek is also a Taiwanese company who is specialized in chipsets for mobile phones and automotive applications. So now Richtek and MediaTek are together, but we still have separate names. So Richtek is really about power management. MediaTek is about chipsets. And in 2017, we did about $460 million US, which puts Richtek in the top 10 of power management IC companies. So we are not a small player in this field. We are located worldwide, but of course our focus is mostly in Asia, because this is where the most of our business is taking place. But we also have offices in the US, and we have an office here in the Netherlands, which is actually just around the corner, on the high-tech campus number 9, just opposite of P0 parking lot. So we have an office and a small lab there. And from this lab, we serve all customers in the Europe region, including Turkey and Israel. We sell power management ICs. Well, power management ICs for computing, like notebook computers, desktop servers, for consumer applications like televisions, set-top boxes, tablets, game controls. We have a lot of parts for mobile phones, networking, telecom, and we have parts for the industrial segment. Now, for IoT, the section of smartphone, basically smartphone is also a handheld kind of an IoT application, and many of the power management solutions for smartphones can be applied also into IoT applications. So let me give you some of the function blocks. Most of power management is really about voltage regulation, to take an input voltage and to regulate it into another application, another voltage. And for this you can use linear regulators, buck converters, boost converters, or buck boost converters. Another segment, of course, is taking the AC out of your AC socket and regulating it into a stable voltage. We use flyback controllers or PFC controllers for that. You have LED drivers, basically making from a DC voltage a constant current, so also power management. We have battery management, basically charging your batteries or checking your battery state of charge by a battery gauge. We have a whole range of the new USB Type-C power delivery, power management. We have audio amplifiers, PMICs, basically a lot of buck converters and boost converters and LDOs into one package. And we have also some sensors. The sensor segment actually comes from MediaTek, and we are borrowing some of the portfolio from MediaTek also to promote as for Richtek customers. So power management, how to select a power management IC. It is really about input and output conditions. So you have an input condition and you have an output condition. For the input condition, you have your input voltage normally, which is important. And for the output condition, it's your output voltage and the output current, which is really important. And based on these parameters, you have to select a certain component. Well, if you have a relatively, well, not very large input voltage stepping down to a output voltage, which is also not too low, so a moderate step-down ratio, you can make use of a linear regulator. Very simple, very cheap, and they have low noise because there is no switching elements. In these applications, the problem is normally the efficiency, because LDOs are basically using heat to dissipate the excess voltage. And therefore, you have also some thermal limitations. LDOs normally are used in applications where you don't have a lot of current or where you don't really care about your efficiency, you have low step-down ratios, and of course in applications that are really noise sensitive, because LDOs can make a very nice, smooth output voltage. If you have a higher input voltage and you need to step this down to a low output voltage, so a high step-down ratio, an LDO is not really a good solution because the efficiency will be very poor. In this case, you will use a buck converter. It's a switching converter which can provide very high efficiency. It also is very flexible because you can make many different step-down ratios. But, okay, it is a switching converter, so it generates noise. And it is more complex because you need an inductor, you need input-output capacitors, feedback networks. Normally you use these in high current applications or applications that really require high efficiency, and in applications where you have to step down from high voltage to low voltage, so high step-down ratios. A buck converter, by the way, is one of the most efficient converters of all topologies. If you need to step up an input voltage to a higher output voltage, you use a boost converter. Basically, stepping up. Again, this is a high efficiency converter because it's a switch mode converter, but it generates some switching noise. You basically use a boost in any application where you need to step up the input voltage to a higher output voltage. If you have an input voltage that can change, for example, a battery during discharging or charging, changing up and down, and your output voltage is just in between this battery voltage range, you need to step up or step down, depending on the battery. Then you use a buck boost converter. Basically, this converter can either step down or step up automatically within this battery range. Again, it's quite efficient. It's also flexible. However, it's making switching noise, and you have a lot of components in one package, which normally means this part is a bit more expensive, and also the efficiency is never as good as a pure buck or pure boost. So you use this basically in battery applications or any application that needs to have varying input and output voltages. So let's have a look at a real IoT application. And we are on the campus, so when I was looking for an idea about IoT, I was just bicycling around the campus and I came along. Maybe the people that are working on the campus, they have seen them. There are actually quite a few cows on the north side of the campus, and they are just grazing, and it's really nice to see them. And from this, I started to think about what kind of application with IoT could you make with them. I talked to the owner of these cows, which is on the Genneperhoeve here. And the Genneperhoeve is around 1.5 kilometers from the campus. And so I asked this farmer, how do you take care of your cows? How do you know what they're doing? And, well, only 20 cows. So he said, well, they take care of themselves. They just need some grass. They're actually, the cows on the campus are young cows, about 1 year old, and they're basically preparing them for giving milk, which means they have to get first a calf in order to have a youngster and to start giving milk. So there is a bull amongst these cows that is taking care of the cows to get them impregnated. But, well, if you have a big farm with hundreds of cows, how can you really take care of your cows? How can you streamline them, make sure they're healthy, and you know where they are, and if they're doing the things they're supposed to do, and if they're not, what to take care, what actions you can take care. So here you have an application. You can, for example, fit a collar to this cow, which is it's not a new application, it's quite standard actually. And this collar then monitors the cow's activity. It monitors the cow's temperature, especially when the cow is in heat. It means that it's ready to be impregnated. You can then take the cow apart and put them together with the bull and let the bull take care of the rest. Of course, the cow also can be checked when they're feeding. Most cows automatically have a feeding machine, and the feeding machine has to recognize this cow and to say how much feed does it need. And also the milking machine can recognize the cow and also check how much milk the cow is giving. So if you have a big farm, you have to streamline your whole process in order to get a good efficiency out of your cows. And of course, this sensor then takes all the data and sends it to the base station, and basically the farmer is sitting next to his laptop and checking what the cows are doing. And this data actually can also be used for other purpose. If you go to a supermarket and you buy milk, you can see that some of these milk have this Better Life sign, which means that this milk has been produced by a cow which is healthy, happy, has good living environment. So the data of all this sensor can be used as a legal proof that your cows are having a happy and healthy life. So how does this application actually look about? So we go a bit more in technical detail. First of all, you need to detect the cow in close range. If it's close to a milking machine or a feeding machine, you have to recognize this cow, which means you need what we call ultra-wideband module. It's a module that uses kind of like radar, sending and reflecting, and thereby able to pinpoint exact positions within about, I think, 10 centimeters. You have to have sensors for temperature and for movement, so accelerometers and temperature sensors. You have to have, well, basically an idea where the cow is grazing, if the cow is moving about, so you have to have a GPS module. And then, of course, you need to send all this data to a farm which is maybe 2 kilometers or 3 kilometers away. So you need a long range and low power wideband system, which is called the LoRaWAN. I think you already had a seminar on this. So these are really the function blocks that are needed in a cow sensor. And of course, you need a controller that is talking to all these different function blocks and switching them on, collecting the data, and then putting the data to the transmitter. And finally, you need a power management for all these parts. And the key point about this power management is it is fed normally by a battery. So if you have a battery, you care about battery life. So one of the first key points of power management is long battery life. You want to extend this battery for as long as possible, maybe 2 or 3 years, before you need to recharge them or maybe swap the battery. Another thing is that it needs to be small, because it has to fit in this small sensor. It has to be able to deal with pulsing loads. Why is that? It's because these applications are normally in sleep mode. When the cow is roaming about, you don't need to measure everything continuously. You need to measure and send data in only short periods of time. And for the rest of the time, most of these circuits will be switched off, which means that the pulse loads that are happening during the active mode, the power management has to make sure that it can take those kind of loads. And finally, some of these blocks, especially the GPS and the ultra-wideband, they are sensitive to noise on the input supply. So you need to make sure that the input supply ripple is not too large. So let's have a look first at the battery. You have, for example, a standard rechargeable battery, lithium-ion type. These have battery discharge currents, which starts around 4.2 volts and then gradually drop, depending on the load here, and they drop finally around 3 volts. This is where really the voltage starts to drop very fast. So these batteries normally range, with operation range from 4.2 volts to about 3 volts. And you can see that when you load them, actually the voltage, this is 5 amps, this is 0.5 amps, so they can take a lot of current. They are high current devices. But they're quite, well, still quite big, relatively big, and you need to recharge them. And of course also this high voltage range may not always be suitable for your end application. A lot of these IoT applications are using this is called lithium thionyl chloride. It's a special type of battery, and this battery is used in applications that don't need recharging. They just put the battery, and the battery has to last for maybe 3 or 4 years. And basically you load these parts at relatively low loads. Here you can see, for example, 1 milliamps up to 50 milliamps. The voltage drops considerably at high load, which means that these batteries have relatively high internal impedance. So you have to make sure that your power management can deal with this. Their range goes from 3.6 volts down to 3 volts. And at 3 volts, you can see it really drops very fast. So below 3 volts, the battery will be almost gone immediately. But your application has to make sure that it can run in this range. Now, if you have applications, many applications still make use of linear regulators, especially the modules inside, they have linear regulators. And you have to understand how that works in order to choose the best power management. For example, take a standard Bluetooth low energy module. It works with well, there is a linear amplifier for the the receiver, a power amplifier for the transmitter, a digital section and an analog section. And most of these sections are regulated by LDOs internally. So if you look at the input voltage range, it has to be powered from the battery. But the module itself, I think I took this from a microchip device, the input voltage range is from 1.8 to 3.6. So basically, this battery range can easily fit this input range. So what you could do is directly connect the battery. But this input voltage range means that the minimum input voltage at these LDO outputs is less than 1.8 volts. So the internal circuits are using maybe 1.6, 1.7 volts. So if you connect the battery directly, which works, of course, you're basically stepping down the battery voltage to a 1.8 volt internal voltage. And this is done by LDOs, which means that all this power is dissipated in the LDO. And that means that you have a lot of power loss. The efficiency here is about 50% because the LDO efficiency is the output voltage divided by the input voltage. And the efficiency at the low end of the battery is 60%. So you have really poor efficiency in your power management if you directly connect these parts to the battery. So if you want to improve your battery life, you have to make this efficiency much better. And you can do that by adding a buck converter. A buck converter has a much better efficiency than an LDO. For example, if you now strip the battery, step down the battery to 1.8 volts, these buck converters normally have around 90 to 93%. So you have very low loss in your circuit because the buck converter in the high range has about 90% efficiency and in the low range even 93% efficiency. So you have much less power loss, which means that you have a much better battery life. There are some other, let's take, for example, this ultra-wideband module. It has internally a 2.8 volt regulation level and a 1.8 volt regulation level, and they have different LDOs for that. Again, the input voltage range will now be 2.8 to 3.6, so you can still connect them directly to the battery. But if you do so, you have, again, a lot of power loss in your LDOs. So again, for this application, you can even use separate buck converters because this section takes most of the power. So using a separate buck converter here definitely makes a lot of sense. And you can also use a separate buck converter for this section, so you still have the high end of your battery also is stepped down to 2.8 in a very efficient way. So if you make power management for these kind of IoT modules, you have to look very carefully in the specification of your module. What kind of regulators are inside? What is the input voltage range? And of course also, what is the ripple requirement, if there is? So in this case, the high efficiency solution is to choose buck converters. You don't need boost converters or buck boost converters here because the input voltage is always higher than the output voltage requirement. So this is just a couple of examples. Let's give you a complete block diagram of IoT. It includes not only the solutions for powering your AP and your modules, also you may have a display. For example, these sports watches now, they have AMOLED display drivers. You may need a battery charger, a fuel gauge. Even you have some sensors here, maybe a biometric sensor. And well, Richtek has components for basically all these yellow blocks. For this demonstration here, I would like to go into detail to the low IQ buck converter and explain you a bit more how this works, because I will take you basically to the lab to show you what you will see on your oscilloscope and how you can optimize this application. So this RT5707, it's a special IoT type. It's a very low IQ buck converter designed for battery input voltage. So the input voltage range is from 2.2 to 5.5, so basically covering any battery chemistry here. You can set the output voltages via these 3 pins because you cannot use a feedback network here by resistors because these will bleed a lot of extra current and you cannot get a good IQ. So everything has to be inside the IC to make sure that it consumes as less current as possible. Then, well, what I mean with less current is 360 nanoamps. 360 nanoamps is really very low. And you may think, why do you need so low? But, well, some of these applications in standby mode only use maybe 3 or 4 microamps. And if your IC is consuming 5 microamps itself, your efficiency in light load is terrible. So to have a low quiescent current of your IC makes a lot of sense because many of these applications are running in sleep mode most of the time. So you see that this application is extremely small. It's a small IC, 0.9 to 1.6 millimeters, so it will fit in any application. And finally, it supports also 100% duty cycle. When your battery voltage is dropping, it will go into 100% duty cycle mode. And finally, it has a fast discharge. And why you need that is basically when you have these low currents and you switch off a converter, the output voltage will slowly discharge. And that basically means you cannot switch it off very quickly unless you quickly discharge the output and you immediately shut down that function block. Also helps to conserve power. I see it's a bit complicated, but basically it's a buck converter. So you have a power stage with a PMOS and an NMOS. You have an LC filter for filtering the output switching waveform. You have a feedback network, and with these extra selection pins, you can actually modify the internal feedback network. Of course, there's a lot of protections on board, and there is a special zero current detection circuit. I will explain you a bit how this works. In high load condition, a buck converter current will be continuous. You see that the current is a sawtooth waveform. When the high side MOSFET is on, the current rises, and when the low side MOSFET is on, the current drops. And the average value of the current is basically your load current. The average value of the switching waveform is your output voltage. So you control the output voltage by basically controlling the on time and the off time. Now, if you go to light load mode, the current drops. So you can see here that the current now goes to 0. And as soon as the current goes to 0, the IC starts to insert a sleep condition. It will ring for a moment and then it will just be floating. And this sleep mode is the key point for achieving good efficiency at light load. Now this looks maybe a bit complicated, and I found that it's easier to understand when you put a real oscilloscope to this circuit. So I apply an oscilloscope to this power management circuit with an input voltage of 3.6 volts and an output voltage set on 2.8 volts. I set the 2.8 volt via this selection here, and I measure the output voltage, the inductor current, and the switching waveform. So this is a Livescope. You can see the switching waveform here. The switching waveform is running steadily. This is the output voltage showing a small ripple, and here you see your load current, which is just above 0. 0 is here. So the load current is continuous. And when you look detailed, you see the load current here, I set it at 200 milliamps, which is basically for IoT about maximum load conditions. The frequency here is 1.2 megahertz, which is the nominal frequency of this converter. And the output voltage ripple is about 18 millivolts, which is still quite okay. Then efficiency I measured here is 94.8%. So even at high load, this converter is really quite efficient. Now, because this is only the period that this converter is working in this way is only when it's active. But in most of the time, the converter will run into much lighter load. So let's reduce the load and see what happens. So now I'm going to reduce the load, and you can see this is dropping. And when it hits 0, you start to see that the converter is inserting these off-time pulses. And of course, it is, in the beginning, it's a bit changing because it needs to find the steady state. But here you see I reduce the load, and now you see in every time there is this little off period inserted, and the current now looks like a small triangle waveform. The output voltage ripple has increased. And why is that? It's basically because the current is discontinuous now, and the switching frequency becomes lower because it has inserted this sleep mode. And with lower frequency, normally you get higher ripple. The output voltage ripple here is 25 millivolts peak-peak. It's some applications, most applications, it's okay, but for some applications, maybe a bit too high. Efficiency, I measured 95.1, so it's still really quite efficient in this mode. Now, this is still 90 milliamps is still quite a high load condition for IoT. So let's reduce the load even further. So you can now see that the off time is stretching, it's stretching and stretching, basically because it wants to reduce the switching losses. During this pulse, there is a transient, a loss period. So it's the switching losses and the conduction losses in this converter that basically result in lower efficiency. But if you insert longer off times, longer sleep times here, you basically minimize the losses. So in this case, we are running at 40 milliamps. The switching frequency has reduced to 103 kilohertz, and the ripple has increased a bit. And why is that? It's because during this load pulse, some of the current, of the load current, is discharging the capacitor. But as the load current gets lower, the discharge section of the load current and the charge of this current pulse, the current pulse charges more and more. So at lighter load, the ripple increases. We try to minimize this by slowly reducing the on time, basically slowly reducing the peak current of the PSM ripple here. Now, during this off time, the IC consumes only 360 nanoamps, which means that during this period, most of the IC is switched off, and only a small part, only this input section, is kept alive and running at a very small 360 nanoamps current. Now, here efficiency is still around 95%, so efficiency really stays very good. But you see that this ripple is quite high, and if you have 36 millivolt peak-peak ripple on a GPS, maybe the GPS range will reduce because of the PLL noise. There's some extra noise inserted into this circuit, which reduces the range or reduces the accuracy. And this is something you have to test or ask the supplier. But if you want to reduce this ripple voltage, it's not very complicated because the ripple depends on the input voltage, output voltage, load, on time, L, and C out. And especially C out is very easy. You just add a small extra capacitor, and thereby you can reduce your ripple. Let me show you. Here I have 10 microfarads of output capacitance, very small, 0402. And now I added an extra 10 microfarads. And you can see now that with this extra capacitor, the ripple has reduced from 36 to 23 millivolts. So reducing output ripple is just a matter of some extra capacitance, which normally is very small. So let's now go to very light load. So this is running 40 milliamps, and really IoT applications run microamps of light load. So I'm reducing the load, I'm reducing the scales. So I just used a variable resistor and reduced the load. Here you can see the IC is reducing or actually increasing the off times, the sleep times, more and more. And at a certain point, I'm running now at around 100 microamps, so really extremely light load. And you can see that the output voltage ripple is still about 36 millivolts. The frequency is now only 144 hertz, so it's really running at very, very low frequency. And this is the key of achieving this light load efficiency, because the efficiency is still around 93%. So even at 100 microamps, you have a very good efficient solution and basically helping you to extend your battery life in this sleep mode. I mentioned that in the sleep mode, this converter is basically running at almost, well, maybe 100 microamps of current, and only during the active mode, this converter has to work very quickly. But it means that the converter has to be able to take this kind of load current. And not all converters can handle that. And to test this, you need to test with pulsing loads. And for that, I actually have a very simple tool. You basically apply a static load resistor and a dynamic load resistor and a MOSFET switch. And this, providing this circuit to your application board, will provide you a pulse current. And then by checking the output voltage, you can check if your converter is running well or not. Basically, because I do this a lot in my lab, I made a little board which is consisting like this. This board is consisting of a small pulse generator, an MCU. It's consisting of a MOSFET switch. I have 7 selectable load resistors, and I have the connections for static load and the connection to my board. I have push buttons for selecting the pulse load frequency and duty cycle, and on the bottom there is this little battery pack, so it can run isolated. You can insert this anywhere in your application. So it generates really fast step loads. And this is very nice because basically applying these kind of step loads to your application will guarantee that any strange things that you see in your application can be simulated by testing with this tool. This tool, by the way, is because I use it a lot and a lot of customers found this very interesting, so we have now made it available to Farnell. So you can also buy this at Farnell. And here I put it, this is the setup. It's very easy. You just hook up the tool to your testing board, apply the battery, and then I select here 22 ohms for 130 milliamp load and 27K for 100 microamps of load. And I measure also that one thing. Normally, when you apply these kind of loads to your system and you use your lab tool, your lab power supply, you easily get resonances in your input because the step load will induce a transient in your input leads, and that can easily lead to resonances. So normally, I apply a small electrolytic capacitor on the input to make sure that my circuit is stable even under these extreme load steps. And here you see it. So when I now apply this tool, you can now see that here I have these little pulse loads. And you can see the converter during the sleep mode is running at low frequency, but during this pulse load it goes into a very high frequency. Here you see the output voltage running in PSM, and during this little step load it will run into a small undershoot. So this is your application active mode, 130 milliamps, and the bottom is your application sleep mode, 100 microamps. And now you can look at your undershoot and overshoot and check if the undershoot and overshoot are okay for your application. Especially the undershoot should be checked. If the undershoot falls too low, it may result in a undervoltage of your modules. So this is something you have to check. So how can that converter actually react, and how does that work? If you zoom into this converter during the step load, you can see that during the step load there is a small delay time, and immediately when the converter sees that the output voltage is dropping, it starts to react. And how fast it can react is basically a measure of how deep your undershoot will go. I measured here around 100 millivolts of undershoot, which is about 3.5%, which is normally still okay. But if 3.5% is too much for your application, well, very simple, add an extra output capacitor. Here I added an extra output capacitor, and you can see now that the undershoot is reduced a lot. So it's very simple. Output capacitor is basically the way to control your ripple and your undershoot. About low battery condition, we have seen already that in this battery condition, the 3-volt level is the critical level where your battery is almost end of life. And if your operation mode goes into that range, you want to make sure that your converter is operating in a defined way. So in this case, my battery voltage is dropping, and you want to make sure that the converter keeps regulating even when the battery voltage is very close to the output voltage. And when it reaches the output voltage, you want to have a minimal voltage drop between the input voltage and the output voltage. And this is what we call 100% duty cycle mode. So in this case, I added now my input voltage, and I slowly reduce my input voltage and see what happens. And basically, when you reduce the input voltage, the converter duty cycle has to become larger. And you can see the converter starts to go into continuous mode again, and now it runs into minimum off time. So in order to reduce the to increase the duty cycle even further, I have to reduce my frequency and keep the off time the same. And you can see that it stretches, and at a certain point, it switches into 100% duty cycle mode. So now, the converter is not switching anymore. It's basically in pass-through mode. So the MOSFET on the high side is directly connecting the output voltage to the battery. And of course, when you increase the battery voltage again, it returns to normal operation. It's maybe easier to look this into a time scale when you let the scope run into roll mode. So here I run the scope in roll mode, and I slowly reduce the input voltage. And you see that at a certain point, braps, there it goes into 100% duty cycle mode. Then I increase the voltage again, and then here it will switch back to the normal operation. So this operation mode, especially here, you see that there is a small hysteresis between the 100% duty entry and the 100% duty exit. And this entry and exit hysteresis is basically to avoid the converter bouncing up and down when the battery voltage is jumping up and down. One thing about 100% duty cycle mode is important to realize is that during the 100% duty cycle mode, the converter is switching on the MOSFET, the high side MOSFET, continuously. And it needs to continuously monitor the input voltage and output voltage in order to make sure that it can switch off the MOSFET again when the input voltage rises. And it means that the converter is always active, which also means there is no more sleep mode, which means that the converter quiescent current is not anymore the 360 nanoamps. So this is something very often not specified in data sheets, but it's something to take care of, especially on buck converters, boost converters, and even LDOs. The quiescent current in 100% duty cycle mode may be different from the quiescent current in the standard PSM mode. So this is, well, one of the aspects of power management in IoT. So low transients, 100% duty cycle mode, and high efficiency. Of course, there is a lot other things that I can tell you about buck converters and buck boost converters and boost converters, but I thought this was a nice introduction to power management. So I would say, if you have any questions or if you want to know more about our portfolio in IoT, please let us know. You can find us on the campus number 9, so very convenient here. So if you have any more questions, please let me know. And hereby I thank you for your attention.